Okay, I have up on the board here what makes a great exam question. Yes, that is a hint. Okay, so we've got E, which is this region that's above this paraboloid, but below the plane z equals 2. So z is the solid region that has a paraboloid as its lower boundary and a portion of that plane as its upper boundary. S is the boundary of E oriented out. One word of caution here, S comes in two parts. Very often people want to say, oh, the boundary is just this portion of the paraboloid, but I need it to completely enclose E. So if I just had that paraboloid, that's like having a bowl. Imagine that I filled it with water and then turned it upside down. The water has spilled. Okay? That's because it wasn't completely enclosed. I need to put a lid on it. If there's a lid on it, I can turn it upside down and nothing spills out because the boundary completely encloses it. So essentially, I'm going to have the boundary S is going to consist of two parts. We'll have S1 and we'll have S2. S1 will be the paraboloid, S2 will be the plane. Okay. So be very careful when you are working with the boundary of a region. Sometimes it is piecewise smooth and comes in more than one part, and you need to make sure to take that into account. I was told this was the boundary of E. So if I was just told S is a part of the paraboloid, fine, it's not the boundary of anything, but I was told this is the boundary of E, so it must completely enclose E. All right, then I have this lovely vector field, okay, and we're asked to calculate the flux of F across S, which is the boundary, two ways. Okay. One as a surface integral, and I'll just remind you that a surface integral along S of F dotted with n ds will simply be the sum of the two surface integrals, F dotted with n ds across S1 plus along S2. So anytime we have a piecewise smooth boundary, we're going to have to integrate along each of those pieces. It's still legal to write this as the double integral along S, but we actually perform the integration by breaking it up into two integrals. Okay. And then we're also going to use the divergence theorem to evaluate the appropriate triple integral. Okay. So we're going to do this two ways. Now, back in the good old days when I gave exams and I was actually in the same room as the students, I could watch their faces as they would do a problem like this. And very often one way is a lot quicker than the other. But, so they'd maybe do the quick way first and then they'd do the longer way. And then you'd sort of see them finishing and they'd be looking back to say, did I get the same answer? Because we're doing the same thing. The flux is the flux. There's one correct answer. So when we do it two ways, we should get the same answer. And I would look at students' faces as they would finish up this problem, and they would range from just absolute ecstasy, yes, I got the same answer, to absolute despair of, oh, my answers don't match. So we're going to very much hope that as we work through this together, we can experience the ecstasy of getting the same correct answer twice. Okay. So I think it's going to be faster to use the divergence theorem because that's going to be one triple integral as opposed to two surface integrals. So what I'll do is in this video, we'll do it using the divergence theorem with the triple integral, and then we'll do the same problem again, but as the surface integrals in the next video. Okay. So if that's my vector field, oh, yes, I did say it was oriented out. Okay. If that's my vector field, the divergence theorem says I can just integrate the divergence over that enclosed region E. So the divergence of F, remember, is del dotted with F. So that's partial x, partial y, partial z, dotted with 2x, 2y, 2z. And of course, we aren't literally multiplying these operators by these functions, but we can apply an operator to a function. So we're getting the partial with respect to x of 2x plus the partial with respect to y of 2y plus the partial with respect to z of, oh, I'm sorry, I wrote 2z a minute ago. It's actually z squared is my third component. So it's the partial of z squared. So that's going to give me 2 plus 2 plus 2z, which is 4 plus 2z. So, according to the divergence theorem, I can just do a triple integral over e of 4 plus 2z dv. All right, and the region over which I'm integrating, remember, is this region that's between this paraboloid and the plane z equals 2. So here there's z equals 2. This was z equals x squared plus y squared is the bottom boundary. If I project this onto the xy plane, I'm just going to get a disk. I'm basically dropping that circle where the paraboloid meets the plane z equals 2, dropping that onto the xy plane and filling that in. That's going to be the region D over which we're going to be integrating in the xy plane, and then we'll be integrating from bottom to top. Okay. Now, that's going to be the disk enclosed by the circle where my two surfaces meet. So this was the z value on the paraboloid, this is the z value on the plane. So I can recognize that D is just a disk of radius root 2. Okay. So I think I'm going to go ahead and set this up in cylindrical coordinates. Okay. So if I do that, theta will go from 0 to 2 pi, and r will go from 0 to root 2. That describes this disk. And over this disk, my z values go from the z value on the paraboloid, that's x squared plus y squared. In cylindrical, that's going to be r squared, to 2. That's the z value on the plane. Then our integrand was 4 plus 2z. No need to change that. X's and y's would have to change to r's and thetas, but z stays as z. And then dv, remember, is going to be r dz dr d theta. We get that extra scaling factor of r. dv would just be dz dy dx, but when I switch to cylindrical, I get that extra factor of r. Okay, so I'm going to just distribute through that r and copy up this integral up here. Integral 0 to 2 pi, integral 0 to root 2, integral r squared to 2. It's going to become 4r plus 2zr, and then we're going dz dr d theta. So if I take an antiderivative with respect to z, I'm going to get 4rz plus z squared r evaluated between 2 and r squared, and then we'll still have to do the integration with respect to r and theta. Okay, so that's the integral from 0 to 2 pi, integral from 0 to root 2 of, when I plug in 2 for z, I'm just going to get 8r plus 2 squared will be 4, so plus 4r, minus, when I plug in r squared, that's going to give me 4r times r squared is 4r cubed, plus r squared squared will be r to the 4th, times r is r to the 5th, and then we still have to integrate that dr and d theta. Okay, so integral 0 to 2 pi, integral 0 to root 2. You can combine those to just get 12r, and then minus 4r cubed minus r to the 5th, just distributing that negative, dr d theta. All right, integral 0 to 2 pi. This is going to become 12r squared over 2, or 6r squared, minus 4r to the 4th over 4 is just r to the 4th, minus r to the 6th over 6. That's evaluated between root 2 and 0, and then we still have to integrate with respect to theta. Okay, integral 0 to 2 pi. Root 2 squared is just 2, times 6 is going to be 12. Root 2 to the 4th, well, That's root 2 times root 2. That gives me a 2. 2 more factors of root 2 give me another 2. 2 times 2 is going to be 4. So minus 4. Minus root 2 to the 6th. That's 3 pairs of root 2. So that's 3 copies of 2. So 2 times 2 times 2, that's going to be 8. So we've got minus 8 sixths. And then we still need to integrate that with respect to theta. So let's see. Notice that this is just 8 right here. And 8 would be 48 sixths. So this is 48 sixths minus 8 sixths. That's 40 sixths, which would reduce to 20 thirds. So all of this becomes the integral from 0 to 2 pi of 20 thirds d theta. And of course, if I integrate a constant, I'm just going to get that constant times the length of my interval, which is 2 pi. So I'm getting 40 pi over 3. So that's what I get for the flux. That's what I got using the divergence theorem. In the next video, we're going to calculate it using the definition of flux as a surface integral over the piecewise smooth surface. And we very much hope, get the same answer.